Welcome to this explainer. When we think of data centers, our minds usually go straight to blinking lights, giant server racks, and endless miles of fiber optic cables. But what if I told you that the ultimate safety of our entire digital world actually depends on perfectly still, unmixed layers of hot and cold liquids? It sounds completely crazy, right? Like something straight out of science fiction. But it is pure, fundamental physics, and it's happening right now in massive tanks all over the world.
To understand how this works, I want you to picture something you've probably seen 100 times. Have you ever ordered one of those beautiful, perfectly layered iced lattes? You get this gorgeous glass where the dense, ice-cold milk sits perfectly at the bottom and the hot, dark espresso rests effortlessly right on top. But what happens if you accidentally bump the table or stir it with your straw? Boom. In a split second, those beautiful layers disappear into a lukewarm, muddy brown mix, and you definitely can't unstir it. Believe it or not, that everyday frustration of ruining a layered coffee is the exact core concept of fluid thermodynamics that dictates how the world's largest data centers survive disastrous power failures.
Okay, let's dive into this. Part 1, the physics of a latte. Just like how cold milk stays at the bottom and hot espresso sits at the top due to density, data center buffer tanks rely on this exact same physics.
So why do those layers even exist in the first place? It really all comes down to density. Cold liquids are heavier and sink, while hot liquids are lighter and naturally rise. If we peek inside one of these perfectly stratified water tanks, we'd find something called the thermocline. It's this razor-thin, totally invisible boundary layer. Below this invisible line, you have crisp, safe, 7 degrees Celsius chilled water just waiting to be deployed. Above the line, you have 15-degree hot water returning from the server racks. You can basically think of the thermocline as a literal invisible shield. As long as that shield remains intact, the incredibly dense and hot server racks are completely protected.
Part 2, the data center's absolute last line of defense, because we are definitely scaling this metaphor up to the massive data center buffer tanks now.
Right, we're no longer talking about a little coffee cup. We're talking about massive tanks holding thousands and thousands of gallons of water. Because the modern internet generates a terrifying amount of heat, these giant unmixed layers of water act as thermal armor. Let's look at an actual emergency scenario. Imagine a severe storm hits and the utility power completely fails. Instantly, the massive mechanical chillers, the machines that actively cool the facility's water, they shut down. Now, even with backup generators kicking in, chillers can take several agonizing minutes to reboot, stabilize, and restart their compressors. In the data center industry, surviving these blind spot minutes is absolutely crucial, and it's called the ride-through. Because the buffer tank is perfectly stratified, pumps can instantly draw the pristine, deeply chilled water directly from the bottom of the tank and send it to the air handling units. The servers don't even know the power went out. The cooling is completely uninterrupted.
Part 3, the fatal danger of lukewarm water. Here's where we introduce the villain of our story, destratification. Just like stirring that iced latte, if the water inside this massive tank starts moving too fast and the layers mix, the entire volume turns into a lukewarm mess. Destratification. And let's look at the stark contrast here. When stratification is maintained, that stable 7-degree supply water reliably guarantees a safe zone for servers, which, desperately require highly stable inlet air temperatures between 18 and 27 degrees Celsius. But when mixing occurs, that lukewarm water simply cannot absorb the immense thermal load fast enough. The water temperature spikes unpredictably. The servers instantly sense the heat, and their internal fans accelerate to maximum speed in an absolute panic to pull in more air, which actually draws more electrical power, generating even more heat. It creates this vicious cycle that leads directly to thermal stress, hardware damage, and an emergency shutdown.
And this brilliantly illustrates Part 4, the magic of space and efficiency. Because this exact water separation dictates the massive spatial and thermodynamic efficiency of the entire facility.
This strict separation isn't just about surviving an emergency. Real estate inside a data center is incredibly expensive. You want to dedicate every possible square foot to data processing servers, not giant vats of water. Therefore, maximizing the usable energy inside the physical volume of your tank is critical. Engineers measure this efficiency using something called the figure of merit, or FOM. In a highly stratified tank, the FOM is between 0.85 and 0.95. This means that because the thermocline is so incredibly stable, a staggering 95% of the total water volume can be effectively used to cool the data center during the power failure. The boundary layer is tight, the cold water is pure, and literally almost zero space is wasted. Now compare that to an unstratified tank with a low figure of merit, anything below 0.7. Because of premature mixing inside the tank, over 30% of the tank's volume is completely wasted. It's just dead space holding useless, lukewarm water. To get the exact same amount of emergency ride-through time as the highly stratified tank, data centers with poor stratification are forced to build massively larger, incredibly expensive tanks, eating up valuable facility space and capital.
And the efficiency gains don't stop at physical space. Keeping that hot return water completely separated at the top of the tank also makes mechanical chillers run far more efficiently. It's a concept based on optimizing the temperature difference, the delta T. Plus, modern data centers use economizers to capture eco-friendly free cooling from cold winter air outside. Stratification perfectly stores this low-grade cold water. If the tank destratifies, the stored water temperature rises above that free cooling threshold, forcing the facility to turn its energy-hungry mechanical chillers back on prematurely, wasting massive amounts of electricity.
Part 5. The engineering that protects the layers. So how do engineers actually prevent millions of gallons of moving water from mixing itself up?
Now, what's really interesting about this slide is how ingeniously simple these engineering tricks are for keeping the drink from stirring. First, they use internal diffusers. These are wide, slotted pipes at the top and bottom of the tank that take fast-moving water and drastically slow it down, gently distributing it outward in a radial pattern. Second, they calculate something called a low Richardson number. By keeping this value above 2.0, engineers mathematically guarantee that the natural buoyancy of the hot and cold water completely overpowers the turbulent forces trying to mix it. And finally, the aspect ratio. You'll notice buffer tanks are almost always tall vertical cylinders. This high height-to-diameter ratio gives gravity the exact vertical space it needs to naturally pull the cold water down and push the hot water up.
It is quite a thing to think about, isn't it? Every time you stream a 4K video, execute a complex financial trade, or access a cloud database, your data is racing through servers running at blisteringly hot temperatures. Yet, behind all the complex code, the flashing lights, and the cutting-edge silicon, the survival of our hyper-fast digital world relies entirely on a beautifully simple physical paradox: keeping a giant tank of water perfectly still. Thank you for joining me for this explainer. I hope this changes the way you look at a layered iced coffee and our internet infrastructure forever. Keep learning, and I'll see you next time.